All right. Let's do it. Good afternoon, everybody. Do we have everybody? Let's see. Leslie's made it in. And Vanessa, Yasmin, and Regina and Wendy, and we got everybody. Okay. There you all are. That's there. That's working. That's posted. And that's running. All right. Awesome. Everything is working for now. Okay. Today, we've been looking at triangles all week, right? Solving different parts of the triangle. And today, we're going to find some special cases where we can solve even more parts of the triangles that are super useful because they are super common. Or perhaps they're super common because they're super useful. I haven't worked out which one's the cause and which one's the chicken, which one's the egg yet. But we could talk about that. Anyways, here's what we're dealing with. The special right triangles. To put this into context, remember the triangle sum. All three angles add up to 180 degrees. So for any triangle, if you were given two angles, you can find the third. Good enough, right? And then for a right triangle specifically, we found with Pythagorean theorem, given any two sides, you could find the third side. And that seemed to work out pretty good. And so one combination or the other, though, doesn't really help you. You have to have all angles or all sides. But in these special cases, now we get to intermix the two. There is, in fact, a cohesive relationship between sides and angles of a triangle. So for the special triangles here, given one side and one angle, you can find the other four measurements. The two other sides and two other angles. Although it's actually three other measurements because one of them is a right angle. The triangles are so special, they must be right triangles. And on top of that, we know another angle and another side. Or sometimes maybe we just know the two sides, but we can infer what the other angles might be because they have to match these right triangles, or these special triangles. That's what's so unique about them. Without any special trigonometric calculation or computation, none of that. You will calculate nothing unless you want to get a decimal approximation, right? But otherwise, the exact form of these solutions, we could just memorize or look up. So here they are. The two special right triangles are the 45, 45, 90, which is also known as the isosceles right triangle. It is the only way you can make a right triangle that also has two congruent sides. And if you have the two congruent sides, then you also get two congruent angles there, which divided evenly must be that is the funniest looking 5 I've ever seen. 45 degrees each. All right? Combined with the other 90, that gives you your sum of 180. And whatever this side is going to match it by nature of being congruent. And if you run through the general Pythagorean theorem, you're going to find the hypotenuse will always reduce down to the other side times, not square root of x, square root of 2. It always comes down to square root of 2. When you have two congruent sides, the hypotenuse is x square root of 2. So there's a little mnemonic there for you to remember that. Two congruent sides or two congruent angles multiplied by square root of 2. That's it. That's the whole special triangle. It's that relationship right there. You could go backwards. Maybe you were given the hypotenuse to start with. Call it y. It was 12 or whatever it was. Well, instead of multiplying by square root of 2, you would then say this is y divided by square root of 2, which you might see written as y root 2 over 2 if you were to rationalize the denominator. It's falling out of favor nowadays. You don't see it quite as often, but these are equivalent terms. I'll let you figure out why. But that's all well and good. What if you say, Mr. Apple, that still seems kind of complicated. Do I really have to just memorize where these things go? The answer is no, you do not. You don't need to memorize this at all. It is given to you. In fact, here once again is the reference sheet from the SAT itself. And right there on the corner, they give you the special right triangles. Right? You are not expected to have to memorize this. You just need to be able to use it, which means whatever side they give you, whatever S, this was 5, well, then the hypotenuse is 5 times the square root of 2. Right? This angle is 45, this one's 90. Triangle sum is enough to tell this has to be 45. But if you can recognize immediately the pattern of, hey, this is a special right triangle, that'll save you time, because you won't have to calculate the triangle sum. You won't have to calculate the Pythagorean theorem. You can just look it up and say, oh yeah, special right triangle, what's the relationship? Here, there, done. And then even faster than that, if you can recognize special right triangle and memorize the relationship, you don't even have to look it up. That's pretty handy, right? It's going to save you a lot of time, a lot of effort. And as I said, these things are so good, we've used these all the time. You see construction sites, right? The fact that this is the only isosceles right triangle comes in a lot of handy when you're building stuff. Okay? It's going to show up a lot. Take apart anything made of wood, you'll find these shapes in there somewhere. Okay? Now along with that, there is a second special right triangle that works out similarly nicely. And that is this guy, the 30, 60, 90. Right? We call this one 45, 45, 90, named after the angles. This one has 30 and 60 degree angles. And it works out pretty nice as well. Notice these two angles, one of them is twice the size of the other. Right? 60 is double 30. Well, look at the sides here. My shortest side across from the smallest angle, whatever that is, x, and my longest side across from the 90, the hypotenuse, is twice x, 2 times x, double the size. So if your angles, if one of them is twice as big as the other, then you have a side that is twice as big as the other. That's a nice, handy little way to remember that and notice that relationship. That's more generalized when you get to trigonometry, right? But here in these cases, that it's such a direct relationship, you don't need to run the trigonometric calculation. That's why they're special. We can take them as a shortcut to trigonometry. And then the third side, the middle child, here across from the 60 degrees, is whatever that short length is. Instead of times 2, it's times the square root of 3, which is somewhere between 1 and 2. How are you going to remember that? Well, I recommend recognizing that the isosceles one has 2 matching sides, so it gets square root of 2. 30, 60, 90 has 3 different sides, 3 different angles, so it gets square root of 3. Right? So once you work out, okay, the special right triangles, they always have one side has the radical. Radical of what? Do I have 2 of a kind? Square root of 2. Do I have 3 different ones? Square root of 3. Right? One angle's twice another, one side is twice another. And vice versa. If the sides are twice the other, you can work out the angles have to be one twice the other. So let me fill that in on my notes here. If we know this has to be a 30, 60, 90 triangle, I already know where the right angle goes. The smallest angle gets 30 degrees. The slightly larger looking one gets 60 degrees. My smallest side is across from the 30. Call that x. My largest side is the hypotenuse. That's double x. So if x was 7, the hypotenuse is 14. Clear. And then across from the 60 degree angle goes something in the middle. X times, square root of, well, this has got the 30 in it, so it's a square root of 3. Any questions so far? Okay. This is pretty much it. Here's these guys. That's what they look like. Try to remember them if you can. If not, just continue to look them up. Again, with practice, that repetition will naturally cause you to remember more and more of it. So just look it up as often as you need as you go through today's exercises. Right? You're finding unknown lengths of these triangles, and then you're using those lengths and angles to find area, find perimeter, find other measurements. Right? Look at number 5 here. They start you out with this funky-looking trapezoid guy, but if you draw a few extra segments in there, it breaks down into, here's a 45, 45, 90, here's a 30, 90, must be 60. Right? You can make the special triangles anywhere you like just by drawing the appropriate segments in. And that lets you solve all kinds of stuff. Speaking of solving stuff, we'll come back to the worksheet specifically later. But I want to roll back to, remember when we were doing surface area and volume, not that long ago, right? And there was that hexagon guy. We had a hexagonal prism and a hexagonal pyramid at one point. And the problem was, they said, hey, here's a regular hexagon. You're like, great, fantastic. You give me the side length and the apothem, and I got you. And then the worksheet was like, haha, no apothem. No apothem for you. And you're like, what? What am I supposed to do? I need the apothem to find the area. Mr. Apple said, you take the hexagon, you divide it up into little triangles. And you're like, okay, I did that. And then I take the apothem right here. And it's at a right angle to the side length. And I'm like, okay, I've got a base, I've got a height. I can find the area of that triangle. Multiply by 6, you get the whole thing. That was the idea. But it turns out, for a hexagon, we can make use of the special triangles as a shortcut and find the apothem length ourselves, just from the side length. Check this out. So I've drawn my apothem in here, right? And by definition, it has to be perpendicular here. Turns out it also bisects the side exactly, so I have 2 equal halves here. So whatever this side length of the hexagon S was, this is S over 2. And I have a right triangle here, right? And what's so special about that right triangle? Well, if you recall, the interior angle of a hexagon, we calculated those way back. Break it up into triangles. You can fit 4 triangles times 180. Divide it evenly among all 6 angles. You get 120 degrees right in here. And when I draw this diagonal in, I cut it in half, which means this angle down here is only 60 degrees. 60, 90. This guy has to be 30. It's a special right triangle. I know the relationship between all the sides now, which means if this is S over 2, that's my short side across from the 30. My long side, the hypotenuse must be double that, double S over 2, and you're back to S. So, side note, it turns out this bigger triangle here is actually an equilateral triangle in the regular hexagon. This is S, this is S, this is S. So we're actually going to find the area of an equilateral triangle. That could be handy in any number of places, right? People love their equilateral triangles. So we'll have a formula for area of an equilateral triangle based only on its side length, and from that get the formula for a regular hexagon based only on its side length. How's that for overkill? And it all hinges on this being a special right triangle, which means we know the length of the apothem here is short side, S over 2, times the square root of 3. So then the area of my equilateral triangle is 1/2 base, doing the whole base now, so it's a full S, times height, S over 2 root 3. And just combine your terms together there, consolidate, and we get S squared times square root of 3 over 4. Nice? And then if you want the whole hexagon, all you got to do is take all that, multiply by 6. Reduce our fraction here, that becomes 3, that's 2, so we get 3s squared root 3 over 2. Beautiful. So now you could go back, and now we can actually work out, oh, that's how you would find the area of your hexagonal base. So you could use that to get your volume of a prism or pyramid with such a base, right? If it's a regular hexagon. Right? Any other shape, you'd have to bring in actual trigonometry, because you won't get the special triangle to work out. But the hexagon is this beautiful symmetry with the six-sided, hexagons are the bestagons, right? Okay, any questions on that then? No? Okay, then a few final comments on the exercises today. Talked about 1 through 6. 7 is area of a trapezoid again. 8 and 9, we're looking at the coordinates of your point. I'll give you a hint here. This is a diagonal line out there. Try creating a few extra segments to turn something into a triangle. Look at this as the hypotenuse of a triangle. And remember, this much is 120 degrees. This much, all the way around, half a circle, 180 degrees. Subtract away to find your angles in there. And number 10, I'm going to call bonus. You don't have to do 10. But if you do tackle number 10, I will actually give you extra credit points on the homework for this one, because it's actually fairly difficult. This is a deep question here. And it's not so much the connection from square root of 18 to 3 root 2. That's just simplifying radical expressions there. It's finding a way to demonstrate that with a single picture. And so you have to see not just the connection between the numbers, but how they connect to the special triangles that we just saw, and how you can demonstrate, how do you show that two things are equivalent in one picture? It really requires you to wrap your mind around many different things at once. So it's a much higher level question, which is awesome if you can get it, right? But I'm not going to require it of you for today. So I'll make that one bonus. This is just a plain old dot grid. You can draw that up or make some regular graph paper on your notebook. You don't need to use this exact space. But it will help you line things up better. And that's about all I can really say on that. Okay? Give it a whirl, because it is a fun one. I liked thinking about that when I read it. I was like, oh, it's a lot deeper than I initially thought. So have fun with it. Otherwise, if there are no other questions on today's work, I'll leave the rest of the time to you.